In section 13.5 we will talk about how to solve trig equations, and this kind of ties together most of what we've done in the earlier section. So you'll be using identities again a lot, and you'll also be using kind of just basically the general algebra techniques that you've used throughout the course, things like factoring and so forth. So we'll see how that works. Just like any other section in this chapter, it all comes down to seeing a lot of these, doing different types of practice. So there are 6 types of equations that you might be asked to solve, and you can see them listed there. 2 of them involve factoring, 3 of them involve identities, and the 4th one, the squaring both sides of the equation, that involves producing identities. So these are techniques, like I said, that you'll have seen before, but certainly a good idea to refresh them and also see how we use equations to solve them as well. So that's what we'll do. Alright, so just the first thing I want to recall is the difference between an equation and identity. An identity is something that's true for every single x value. So for example, this right here is always true no matter what numbers you plug in for x right there. It will always be true that 2x plus x is 3x. On the other hand, some other expressions like this one, if we were to solve this right here for x, there's only a few x values. In this case, there's only one x value that makes that true. So that's the important thing to note. When we solve these equations, we're going to have only a few answers. It's not quite the same as what we've been doing earlier in the chapter, which is solving identities. Okay, so we said there's 6 types of equations, and there's this sheet that you have that kind of shows them to you. So the first thing that you have to do is you have to decide which strategy or which method do I need to use, because obviously, that's just like kind of solving a puzzle. You're trying to find out where the pieces fit together. You have to make sure that you're in the right region of the puzzle before you start putting that piece in that particular spot. So if we look at this, we have a bunch of strategies. The first 2 say double angle and half angle, and we can eliminate those right away because a double angle would look like this. If there's a 2 theta, or if there's a theta over 2 somewhere in that equation, that means we're dealing with a double angle or a half angle, but in this case there are neither of those, so we're not going to do that. Okay, next one is factoring the greatest common factor. If you look at this, it does have a greatest common factor because in both of these parts of the expression there's a cosine. So we can factor out a cosine theta, and if we divide this here by cosine theta, those will cancel and be left with sine theta. And then if we divide this here by cosine theta, those will cancel and be left with minus 1/2, and that's equal to 0. Okay, now same as where we would solve a regular algebra equation. So if we were asked, let me just sidebar this, suppose this is a totally separate problem. Suppose you were asked to solve this, and the way you would solve it is you would see what x value makes that 0 and what x value makes that 0. Same idea right here. We want to set both parts of this equal to 0 and then see where that takes us. So let's start with the right side first. We can solve this for sine by adding 1/2 to both sides. So we get the sine of theta equals 1/2, and then we can solve for theta by taking the inverse sine. And we need to be aware that the angle that has a sine of 1/2 is 30 degrees. So theta is 30, but then we also have to look what they're telling us. They're saying that theta is between 0 and 180. So 30 is not actually the only angle that has a sine of 1/2. Okay, just to remind you, here's a unit circle. Here's a 30-degree angle right here. And remember that sine on the unit circle is the y-coordinate. So sine is the same thing as the y-coordinate. But notice if we were to go over here to the second quadrant, that is the same y-coordinate right there. That has the same vertical height. And the question is, what is this angle right here? This large yellow angle I'm about to draw. That's the one that we want. And the answer is, well, it has the same exact reference angle as this one. That has a reference angle of 30. So how do we find the yellow? The yellow has to be 180 minus 30 because the yellow is almost going all the way to 180 except for that last 30. So 180 minus 30 would be 150 degrees. So on many of these trig identities, there's going to be multiple answers or multiple parts to the answer. So that's at least the first part. Alright, the next thing we need to do is we need to we need to be able to find the cosine portion as well. So it says cosine of theta is equal to 0. And actually for that we can just look at the unit circle. Cosine is the x-coordinate, and the x-coordinate is 0 right here, because on a unit circle that's the point 0, 1. It's also 0 right here. And this is 90 degrees, and this is 270. So both of those would be answers, but notice they only want angles, they tell us, between 0 and 180. So we only have to take the 90 as our answer. So those are our three solutions. 30 degrees, 90 degrees, and 150 degrees are the answers. And we could test those by plugging them in. And we get, plugging them into the original equation, we would get something true. Alright, so that's an example of factoring the greatest common factor. Okay, now in that previous example, again, notice they told us solutions between 0 and 180, but this is what this means right here. Suppose that we just found a solution that was 30 degrees, right? So here's 30 degrees, and we said that was one of our solutions. But think of it this way: if I were to go at 30 and go all the way around again, well, that's also a solution to that equation. That would be an extra 360 on top of 30. And then if I did that again, so I'm at 390 degrees and I go around another 360, well, now I add another 360, that's 750. That would also solve that equation. So what this means right here is that the solutions that you get, if you get 30 degrees of solution, in reality you're also getting any multiple of 360. Okay, so if you ever see what I just wrote there, if you see 30 degrees plus 360 times k, this basically means that picture that I just drew. It means not only is 30 degrees a solution, but any rotation, any extra 360 degree rotation, that's also a solution, because 390 degrees or 750 degrees or the reverse, you could also subtract 360. Those would all be solutions to that equation. For example, the sine of 30 in the previous example, we said that's 1/2. But the sine of 390 degrees is also 1/2. The sine of 750 degrees is also 1/2, because all of these are just an extra rotation of 360 on top of 30. So that means you're basically leaving off exactly where you started. Okay, and then the other thing they mention is if you're doing it in terms of radians, 30 degrees in radians is pi over 6. So instead of saying plus or minus 360, you could say plus or minus 2 pi. And the k right here stands for the number of extra rotations. So if k is 1, we'd be doing 1 extra 360. If k is 2, we'd be doing 2 extra 360s, or 720, and so on. So that's just to note in case you see any notation like that. Okay, and this is an example. It's going to say solve this for all values of theta if theta is measured in radians. Okay, so this is not really one of the techniques. This is just kind of solving a basic equation. Sorry, that's supposed to be a -1 right there. So we get cosine of theta equals -1. Where does that happen on the unit circle? Here's our unit circle. Cosine, remember, that's the x-coordinate. And the x-coordinate is -1 right here. That's the point, sorry. That is the point, -1, comma 0. And that occurs at 180 degrees, but they're asking us for values in radians. So we have to remember how to convert radians, or degrees to radians. Those will cancel, and that's the same as pi radians. So here's the answer. Theta equals pi radians plus or minus any amount of rotations that we want to go. So for example, if we were here at 180 and then we do another 360 degree rotation, well, that's also going to be a solution. That's 540. Okay. If we're at 180 and let's say we go backwards, so we go clockwise instead, well, that would be minus 360 from that, so it would be -180. And there's an infinite number of solutions. If you rotate as much as you want, you're always going to get a solution. So in order to say that, we could say the number of rotations, each rotation is 360 degrees, but we're dealing with radians, so I'm putting that as 2 pi radians. And then k stands for the number of rotations. That means if we're at 180 degrees, if I rotate once, twice, 3 times, every time I'm doing that, I'm adding 2 pi, or I'm adding 360. And k is how many rotations I want. So all of this means right here is that the solution to that equation is pi radians, or 180 degrees, plus or minus however many rotations of 360, or however many rotations of 2 pi we wish to include. That's just the key part of that answer is pi. Obviously, the plus or minus 2 pi k just says you get the same solution if you just kept rotating over and over again. That's all that that means. Alright, let me show you a couple other techniques here. So we go back to our sheet, double angle and half angle identities. So double angle identity, a good example of that would be 2a right there, you can see. So actually let's look at 2b first. So 2b is a little bit easier. 2b says solve 2 sine theta equals -1. So you can see the solution is right there. Let me just fill out some of the steps that are missing. If you divide both sides of this by 2, you would get this right here, sine theta equals -1/2. Remember that the angle that has a sine of 1/2 is 30. So this, we kind of did this problem before, 30 degrees, that has a sine or a y-coordinate of 1/2. But also remember this acronym, all students take calculus. This right here, this is a -1/2, and sine is negative in these two quadrants, which means that it will also, both of those angles that have a sine of -1/2 are going to have a reference angle of 30. And the question is, what are the actual angles? Well, this one in yellow is going to be 180 plus that extra 30, and that gives you 210. And this angle in orange right here is going to be almost all the way around, almost 360, except for that last 30. Then 360 minus 30 gives you 330. So those are the two solutions for 2b. 2a is the one I want to show you. That is the double angle one. And again, how do we know there's a double angle? Because that's what this means right here. 2 theta is you're doubling theta. And so for that, we need to remember our identities for double angle, for cosine. Cosine of 2 theta actually has 3 versions for its identity. In terms of which one do we want to use, and it kind of tells you on the sheet here, we're using strategy 1, the double angle identity. The one that we want to use is the one, I don't know if they show you here, I don't think they do. We want to use the one that has nothing but cosines in it. Okay, and that's because the rest of this equation has a bunch of cosines. So let me rewrite this example. I'm going to use the identity that looks like this. Cosine of 2 theta is equal to this. Remember, there's 3 versions. Why am I using this one? Because the rest of the equation has cosines in it. So if we see, we want to basically keep them all to be the same trig function. So keep everything as cosine. So this right here is getting replaced with that. And then I'm going to write the rest of the equation. Plus cosine theta, that's coming from right here. And plus 1. And that's equal to 0. Okay, now let's simplify this. We have 2 cosines squared. This minus 1 and that plus 1 basically cancel each other out. So we're left with cosine. And now this is actually the strategy that we talked about before. This is another greatest common factor problem, because both of these have a cosine in common. So let's pull out the cosine. If we do that, we're left with 2 cosine plus 1. I'm dividing each of these things by cosine. And now we can solve it the same as what we saw before. And they're asking us for all values if theta is measured in degrees. So I'm going to have to do one of those plus or minus 360k to show that it's covering all values, not just the one that we find. So we'll set this thing equal to 0, and we'll also set this thing equal to 0, because it's telling us it equals 0. And then we'll subtract 1 from both sides. We get 2 cosine is equal to -1. We'll divide that by 2. We get cosine of theta is equal to -1/2. Where does that occur? Well, hopefully at this point in trigonometry you've memorized this table right here. And remember that the 3 angles that are important to know are 30, 45, and 60, and the sines count up and the cosines count down. So the cosines go radical 3 over 2, radical 2 over 2, and 1 over 2. That means cosine of 60 degrees is the thing that has a value of 1/2. Okay, the only problem is this is negative right here. So we need to be in the 2 quadrants where cosine is negative, and cosine is negative in the all students in the students quadrant and in the tangent quadrant. All students take calculus. So that means in both of these quadrants we're going to have reference angles of 60 degrees. And again, how do we know it was 60? Because in this table it's the 60-degree one that has a cosine of 1/2. The reason it's negative is because we're in quadrants where cosine, which is the x value, is negative. Quadrant 2 and quadrant 3, okay, when you're to the left of that line, cosine is, or x value is negative there. So what is this green angle? That's going to be 180 minus 60. which is 120. So that's our first solution right here. And then our next solution is going to be this one. It's going to be this purple one, which is 180 plus an extra 60. And 180 plus 60 is 240 degrees. Just write that right here, 180 plus 60. So those are two of our solutions. We'll come back to that in just a second. Let's look at this other one. The cosine of theta is equal to 0. Cosine is the x-coordinate, and x is 0 right here at 90 degrees. And it's also 0 down here at 270 degrees. So those are our other two solutions. So theta equals 90 and theta equals 270. Okay, so that's really that's the answer, but we have to kind of be aware of how they want us to write our answer. They want us to write our answer in terms of for all values of theta. So here's how you can say it. It's this one right here. Okay, you can say, and you can kind of see how they wrote it right here. Let me just circle this so it's easier to say. So 120 plus rotations of 360. That's what this says right here. Plus however many rotations of 360 you want to do. And they didn't do plus or minus because k can also be negative. You could do clockwise rotations. Again, all that means, just to emphasize, is that if I'm here at 120 and I go around 360 and around again, that's what this says right here. 360 times k says we can circle around 120 as many 360 rotations as we want. We'll always get a solution that means the exact same for that equation. So that takes care of the 121. Here's how they wrote the 241. That's 240 plus or minus as many 360 degree rotations. Now here's the question, why did they only write 90 here instead of 270? And here's why. Because they covered it by saying instead of k times 360, they said k times 180. If you're at 90 and you go around 180, well, there's the other solution, because 270 is 180 degrees from 90. So you could either write it like this. You could write 90 plus 360k, and you could write 270 plus 360k. That's not wrong, but a faster way of writing this is the way they wrote it right here, because for that solution you're running into a solution every 180 degrees. Alright, this one's a little bit more basic. It's not really using identities, just using a word problem. So this talks about a Ferris wheel that has a diameter. Let's see if I can draw a Ferris wheel here. Here's a Ferris wheel. It has a diameter of 40. And I'm not going to try to draw the seats. You can use your imagination. It turns at a rate of 1.5 revolutions per minute. The height above the ground in meters is given, when you ride a Ferris wheel, and turns at a rate of that many revolutions per minute. So if it's 1.5 revolutions per minute, well, they might ask us in a sec to talk about how many seconds that is. We'll deal with that in just a sec, although possibly not. They pretty much give you the equation right there. It says the height is given by that right there. And the question is, how long after the Ferris wheel starts will your seat be 31 meters? So that basically means find when h equals 31. And the way that we can do that is solving as we would normally solve an equation. We'll subtract 21 from both sides. So again, if this is a height of 40, that means this down here, we're assuming it's a little bit above the ground. I'm not sure, they tell you how much above the ground. It looks like 21, but we're not quite at the top. We just want to find out how long until we're at a certain point. So those go away. We get negative 20 cosine 3 pi, and I'm going to use a capital T for time because sometimes it looks like a plus sign if you don't do that. We'll divide by negative 20, and so we're going to be left with this. We're going to be left with 10 over negative 20 reduces to negative 1/2. And we have cosine of 3 pi times t. Okay, we want to cancel out the cosine, so we can do that by taking the inverse cosine. So those will cancel. And the inverse cosine of negative 1/2, we kind of just found that a second ago in that other problem. So let's just go back and remind ourselves. The inverse cosine of negative 1/2 was those two angles right here. It was 120 and 240. But notice that we're dealing in, and if you're not sure how to tell, they're giving you pi here. They're telling us that we're dealing with radians, not degrees. So we know that our 3 pi over t, this thing right here, it's going to equal 120 degrees and 240 degrees. We want to change those into radians. So let's do that real quick. So So 120 times pi over 180. 60 goes into that twice, and it goes into that 3 times. So that's the same as 2 pi over 3. That's what this equals right here. And since 240 is twice as big as 120, it means that's going to be twice as big as 2 pi over 3, which is 4 pi over 3. So here's our two equations. 3 pi t equals that, and 3 pi t also equals this. How can we solve for t? We can divide by 3 pi, and dividing by 3 pi is like multiplying by 1 over 3 pi. So let's do that on both sides. So 1 over 3 pi. The pi's will cancel here, and we're left with 2 over 3 times 3, which is 2/9. So t equals 2/9, and right here the pi's will cancel, and we're left with 4 over 9. So t equals 4 over 9 as well. Now here's how we need to interpret that. T, I believe, is given in minutes. We look up here. Do they tell? Yeah, we're talking about revolutions per minute. So t is given in minutes. So this answer basically means 2/9 of a minute, and that turns out to be about, what is that going to be? 13 seconds maybe. 120 divided by 9. That turns out to be, what is that? 13.3 seconds. And then we also had 4/9 as our other solution. So 4/9 turns out to be 26.6 repeating seconds. 26.66666. Alright, so 31. So that basically means, like, if you're on the Ferris wheel, maybe that's 31, and then you reach 31 again because your Ferris wheel is kind of going this way. So it makes sense that we would have two solutions right there. Alright, the last part I want to show you is just a couple more of those methods that we haven't talked about. So some trig equations don't actually have a solution. Here would be an example, the cosine equals 4. Why does that not have a solution? Because on a unit circle, notice that these 4 points show us the maximum and the minimum values of sine and cosine. So this point is 0. Sorry, that point is not 0. I always do that. That's 1, 0. That's 0, 1. This is -1, 0. And this is 0, -1. Notice that the biggest value of cosine is 1. The smallest is -1. Biggest value of sine is 1. The smallest is -1. So there is no angle that has a cosine of 4. That's impossible. Sometimes when you do these equations, you might not have any solution. So let's bear that in mind as we solve these, or at least part of it. Usually, for a lot of these, you'll have at least some of it having a solution, but not all. So let's look at this. This is a technique we haven't done yet. There is no double or half angles in this problem, so we're going to skip those. There's no GCF. Strategy number 4 is factoring a trinomial, and this is actually a trinomial. If you don't see it, then here's a way that it might become a little bit more visual. Suppose that we replace sine with a letter like x. So 2 sine squared would be 2x squared. 3 sine would be 3x. And -2 would just be -2. So notice this right here is something like what we factored in prior chapters. That's a trinomial. So if you want to, basically what you can do is just change it like we just did and factor it and then replace the signs later. So we know to get 2 sine squared, we're going to have 2 sine times sine. That's the only way to get that. We know to get -2, it's got to be, one of them has to be positive, one has to be negative. We don't know which is which though, so let's try the minus here and the plus here. And 2 is a prime number, so let's put 2 times 1. Okay, if you switch those around and you got it wrong, you can check it by using FOIL. So let's briefly check. 2 sine times sine is 2 sine squared. So that's right. 2 sine times -2 is -4 sine. 1 times sine is plus sine. So notice -4 sine plus sine, that's going to be -3 sine. So that does work. And then 1 times -2 is -2. So that's how you can check it. Okay, now we know it's equal to 0, and we also know that we're between 0 and 360. We're 0 and 2 pi. 2 pi is the same as 360, the radian equivalent of that. So let's set both parts of this equal to 0, and now we're going to solve it like we solved the other one. So you can see a lot of these have the same pattern. Let's start with this one. We'll add 2 to both sides. Sine is equal to 2. And you might notice from the way that they titled this problem, determine whether a solution exists. A solution does not exist for this. And you can test it. If you plugged in inverse sine in your calculator, I'll do that in just a sec just to show you. Remember, on the unit circle, the maximum value of sine is right here. Sine never goes above 1. So this this right here has no solution. And just to prove it to you, I'll put it in the calculator. We'll do the inverse sine of 2, and we should get an error. Make sure we're in degrees here. Actually, in this case, we probably should be in radians, but it doesn't matter for this problem. So inverse sine of 2, and you can see you get an error. That's impossible because there is nothing. Remember, sine is opposite over hypotenuse. That would be like saying the opposite side is twice as big as a hypotenuse, and that's impossible. Hypotenuse is the biggest side in a triangle. Okay, so that one has no solution. This one, though, will have a solution. We'll subtract 1 from both sides, and then we'll divide by 2. Sine equals negative 1/2. So sine equals positive 1/2 at 30 degrees. Sine of 30 degrees is 1/2. So we know our reference angle is going to be 30. But the question is, in which quadrant are we going to be in? Sine is negative 1/2, and sine is negative in these two quadrants, in quadrant 3 and 4. So we need to find out what this angle is, but in those two quadrants right there. So that's going to be this angle, 180 plus 30, and that's 210. And then we also need this angle right here, which is 360, except for that last 30. 360 minus 30, which is 330. So those are our two solutions right there. Theta equals 210 degrees or 330 degrees. And if you change those to radians, I think they wanted you to at the beginning. They said yes, if right here they're telling us in radians. So if you change this one to radians, it would turn out to be 7 pi over 6. And this one, if you change it to radians, would be 11 pi over 6. Again, just to remind you how you do that, you do the number that you're trying to change times pi over 180. And when you simplify that out, you'll get what I just showed right there. So those had two solutions. Remember that this one right here doesn't have a solution because sine is never more than 1. All right, let me show you some more techniques here. So just going through our sheet, we've done a double angle one. We haven't done a half angle. We'll get to that. We've done a GCF. By the way, some of these you might have to use several strategies in one from time to time. I think we've had to do that a couple times. We did a trinomial. Pythagorean identity. Well, that's not this one. It will be a next one. But I want to show you the last technique there, number 6, squaring both sides of the equation. If you look at this right here, it almost looks like at least something involving our most well-known Pythagorean identity, which is this one right here. That's the best known Pythagorean identity. So the problem is this: we can't use a Pythagorean identity unless sine and cosine are being squared. And so that's why this technique, number 6 on that sheet you see right there, is called squaring both sides. The reason we square both sides is so that we can make this appear. And right now we can't make it appear until sine and cosine are being squared. So if you look at this equation right now, there's no way to solve it. We can't do anything with that in its current form. The only way that we can get a Pythagorean identity to appear is if we square both sides. So that's what we're going to try to do. Okay. The one thing you have to be aware of is when you square both sides, you sometimes introduce what's called an extraneous solution. So at the end of this problem, we're going to have to take our answers, plug them back in, check and see if we got one of those. Okay, so let's start by squaring both sides. Again, why are we doing this? Because we want this identity to appear. And that identity has sines squared and cosines squared in it, not just regular sine, regular cosine. So the left side will be sine squared. This one, remember that you have to FOIL this. Don't just do 1 squared plus cosine squared, because you'd be missing a term right there. So when you do that, you're going to get 1 plus the outside will be cosine plus another cosine. That would be 2 cosine. That's the outside plus the inside terms. And then this will be plus cosine squared. Okay, now this technique that we're about to use is one we've used before. It's technique 4, which is factoring a trinomial. The only problem is we want everything to be a single trig equation, or single trig function. And because there are mostly cosines here, and particularly because it's cosine of the first, we want everything to be a cosine. So that means we have to change this thing in terms of a cosine. We can do this using this identity right here. If we were to solve that for sine squared, we would get this. Sine squared equals 1 minus cos squared. That means wherever I see a sine squared, I can replace it with this right here. And that's exactly what we'll do, because that will give us everything in terms of cosine, which is what we want. Okay, so now we have this. So let's move everything to the other side by subtracting the 1, adding the cos squared. We'll subtract the 1, and we'll add the cos squared. So when we do that, we're going to get 0 equals, well, those cancel, and we're just left with 2 cosine plus cos squared plus cos squared is going to be 2 cosine squared. Okay, so that right there, now you can see, I actually said it was a trinomial one. It's actually the method 3, which is factoring the GCF, because the 1's disappeared. So if you look at this now, this has a greatest common factor of 2 cosine. And how do we know that? Because they both have a 2, and they both have at least 1 cosine. So 2 cosine, if you divide this thing by 2 cosine, you're just going to get 1. If you divide this by 2 cosine, you're just going to get cosine. And now we can set each of these equal to 0 and solve like we've been solving from before. So let's do this one first. It's a little bit easier. Cosine is equal to -1. Where does that happen on a unit circle? Cosine is the x-coordinate, and the x-coordinate is -1 only at that point right there, which is 180 degrees. So there's our first solution. Theta is 180. This one, if we divide by 2, we get cosine is equal to 0. Remember that cosine again is the x-coordinate, and the x-coordinate is 0 right here at 90 degrees. So there's one solution. And it's also 0 right here, and that's at 270 degrees. So that's our second solution. Okay, so in this equation, it looks like we had 3 solutions right there, but it is important to check them to be sure that we wind up with non-extraneous solutions. So if we go back to the original was sine equals 1 plus cosine. So I'm just going to write this down here so we have more space. So here's the original, sine equals 1 plus cosine, and we have to check all 3 of these. We have to check 90 degrees, we have to check 180 degrees, and we have to check 270 degrees. Because why are we doing this? We might have gotten an extraneous solution in one of these. So let's start with 90. So sine of 90, does that equal 1 plus, we're plugging into this equation right here, 1 plus cosine of 90. So here's our unit circle, and 90 is up here. Cosine is the x, and sine is the y. So the sine of 90 is 1. The question is, does that equal 1 plus cosine of 90 is 0? And that does work. So 90 is a true solution. We'll keep that one. Okay, then we have to go to 180. So the question is, does sine 180, does that equal 1 plus cosine 180? Sorry for the mess there, running out of space, but here's 180, and the cosine is -1 there, and the sine is 0 right there, because cosine is the x and sine is the y. So the sine of 180 is 0. Question is, does that equal 1 plus cosine of 180 is -1? And that is true. 0 equals 1 plus -1. So we're going to keep the 180 as well. So we have 2 of these solutions that work for us. Let's try the last one. Sine of 270, does that equal, just move that over a little bit, does that equal 1 plus cosine 270? Well, this 270 is down here, and the cosine right there is the x, which is 0. The sine right there is -1. So the sine of 270 is -1. Does that equal 1 plus cosine of 270 is 0? And this is wrong. 1 plus 0 does not equal -1. So that's an extraneous solution. So your final answer only has 90, and it only has 180. You don't include the extraneous, because when we plug it back in, it doesn't work. Okay, that's the main idea right there. All right, a couple more to show you here. So out of these, I just want to pick. Let's see which one looks more interesting here, because I just want to see if there are any techniques I haven't shown you. Well, let's just take a look at each of them. I think I might actually have the answers already written here, so I can just show you those. Here we go. All right, so on the left side is 4a. You can see what we did here. We wanted to use this technique, which is using number 5, using a Pythagorean identity. And the most famous identity, the one that we use so often, is this one right here. So you should probably immediately think of that. When you see a sine squared and a cosine squared, you want things to be in terms of one trig function. So since we have, it doesn't really matter how you do this, but since we have 2 cosine squared, we just changed sine squared into this by going up here. If we subtract cos squared from both sides, we would get sine squared equals 1 minus cosine squared. Then we combine the like terms, so minus cosine squared plus 2 cosine squared gives us this. And then we still have this 1 right here. We subtract the 1 from both sides, and that gives us this equation here. If you square root both sides, you get this. Cosine theta equals plus or minus radical 3, and that's a problem. Radical 3 is the number 1.732. So this is saying cosine equals plus 1.732 or minus that, and that's impossible because on a unit circle, cosine is the x-coordinate, and the x-coordinate's maximum value is right there. It never goes above 1 or less than -1. So that means this equation 4a has no solutions at all. Okay, that has no solutions. Okay, you can already see on the right side this actually has an infinite number of solutions. So we started by replacing this with 1 minus sine squared, and that's from this identity up here again. Okay, then this is supposed to say sine squared right here. Okay, then what do? We add sine squared to both sides if we want to, or really they just rearrange it here by doing 1 plus 3, which is 4, and you can see we get something that's, one side is equal to itself. That's an identity. That's true for every single number. If the left side turns out to be identical or equal to the right side, then you have a case where all solutions are possible. So that's all real numbers. Okay, and this is just going to show you, these last couple pages will show you the last couple techniques that we haven't really done. So this is technique number 5, using a Pythagorean identity. How do we know? Because none of the other techniques work. If you go down the list, there's no double angle, there's no half angle there, there's no GCF, there's no trinomial. We can't square both sides because both sides, things are already being squared here. We don't want to square it even more because you have something to the 4th power. So essentially the only thing that would make sense here is to use a Pythagorean identity. Okay, and if you remember secant squared, there's an identity for secant squared and tangent squared, which is this one that I just wrote. Sec squared equals 1 plus tan squared. So we're going to be using that one. Let's replace every sec squared we see with 1 plus tan squared. Okay, and the reason we're going to do that is because it would be kind of hard to do that with tan to the 4th. Since we already have something with tangent, it's tan to the 4th. Let's take the secants and replace those with tangents rather than vice versa. Okay, so we have this, and that's equal to -1. Okay, then let's distribute. So we have 2 plus 2 tan squared minus tan to the 4th equals -1. And then let's move everything to the right side just so we can get the biggest exponent thing being positive. So we'll add tan to the 4th, we'll subtract 2, and we'll subtract this thing right here. You didn't have to do it this way, you could have moved it to the left side, but doing that in part so that the tan to the 4th is positive. So this is going to equal tan to the 4th minus 2 tan squared. I'm just writing this in descending exponent order. And then -1 minus 2 is -3. Okay, so we started with technique 5, and I told you that a lot of these will be multiple techniques. We started with technique 5 using a Pythagorean identity. Now the next thing is going to be technique 4, factoring a trinomial. And you can see this kind of looks like a trinomial. If you're not clear on why that's true, then replace any tangent that you see with an x. So tan to the 4th would be like x to the 4th. 2 tan squared would be like 2x squared, and minus 3 would be -3. So we know how to factor this from chapter 4. What numbers multiply to -3 and add to -2? That would be -3 and +1. And the only problem is x times x is not going to be x to the 4th, so I need those both to be x squareds. So let's do that over here, except instead of having x's, we'll have instead of having x squareds, we'll have tangent squared. So tan squared minus 3 times tan squared plus 1. I'm just using this thing right here, using that same pattern. Okay, now we're in a position to be able to solve this. So tan squared minus 3 equals 0. We'll set that equal. And tan squared plus 1 equals 0. Let's start with this one because this one is a little bit easier. Tangent is tan squared equals -1. If we square root, we're going to get square root of a negative, and you can't do that. And you get a real number anyway. So this part has no solution. There's nothing that when you square a tangent you would get -1. Okay, this does have a solution though. If we add 3 to both sides, we would get tan squared equals 3. Square root that and put a plus or minus in front. And tangent equals plus or minus radical 3. Okay, well you may recognize that from the table that we have committed to memory. So sine and cosine, we we already know that the sines count up and the cosines count down. So I'm just going to write this real fast. So sines count up, 1 over 2, root 2 over 2, root 3 over 2. This one goes root 3, root 2, and 1 over 2. Remember that tangent is sine over cosine. So the easiest one to learn is 45 because it's radical 2 over 2 divided by itself. Sine of 30 is radical 3 over 3, and tangent, I meant to say, and then tangent of 60 is radical 3. So this right here is actually going to have 4 solutions because there are 2 places where tangent is positive radical 3, and that is in the 2 places where tangent has reference angles of 60. So one of them is right here, and all students take calculus. The other place where tangent is positive is in this quadrant right here. You can see that red line. Tangent's like the slope. It's sine over cosine. Sine is the y, cosine is the x. So it's like you can see the slope in those 2 red zones that I just put is identical. Okay, so let's get our 2 solutions. And we have one of them being 60, and the other one is 180 plus that 60, which is 240 degrees. So there's our 2 solutions for the positive radical 3. How about the negative? Let's use blue just so it stands out a little bit better. So that's going to be right here and right here. Both of those are reference angles of 60. And again, we know this because tan of 60 is that number, radical 3. So that angle is going to be 180 minus 60, which is 120. And this angle here is going to be 360 except for that last 60. 360 minus 60, which is 300. Those are your 4 solutions. The nice thing is you don't have to check them in this example because we didn't at any point in this equation square both sides. We only have to check when we are squaring both sides, and in this example we didn't. So we know that as long as the rest of our math was correct, we should get the right answer. Okay, so those are our 4 solutions, and they do say all values. So if you want to simplify that, you could say 60 plus 180 times k, and you could say 300. Actually, let's fix that right here. So the reason I'm saying this 60 plus 180k, notice that this is a solution. If I go 180, that's another solution. So basically anytime I'm looping 180s, right, I'm always kind of coming across that 60. That's such a mess you can't read it now. And then the other solution would be see if you can still make this out. The other solution would be this 60 right here, and then if I go another 180, I'm at a solution. I go another 180, another 180. So this version of the 60, that was 120 degrees. That was 180 minus that blue 60. I apologize for the mess. So we could write this as 120 plus 180k also. But if you just wrote those 4 original solutions in most problems, they're going to ask you from 0 to 360, so that's okay. I believe there is 1 or 2 more that I want to show you. Let's do one of these because just to get the extra practice. So this would be an example of strategy 5 using a Pythagorean identity. If you try any of the other ones, you'll go down the list: double angle, half angle. None of those things are going to apply to this example. So the only one that would actually work here is going to be using a Pythagorean identity. And let's see which one would be best here. Let's do 5b, I think would be best. So the identity, when in doubt, when we're dealing with identities, change everything into sines and cosines. So cotangent is the same as cos over sine. That's an identity. And then we still have this plus 2 sine squared. So let's fix this a little bit. Let me get rid of this here for a sec. Okay, so dividing by a fraction is like multiplying by the reciprocal. So the reciprocal of cos over sine is sine over cos. Those cancel, and we're left with 2 sine squared equals 0. So now this is sine plus 2 sine squared. If you go back to that sheet, the technique that we would use here is a greatest common factor, because we can see that they both have a sine in common. So if I pull out a sine, I'm going to be left with this right here. And now this is an equation similar to what we've solved on many previous examples. So let's just do that real quick. So we'll set the sine part equal to 0. We'll set the parentheses part equal to 0. Sine equals 0. Remember, the sine is the y coordinate. Sine is 0 right here and right here. And that's at 0 degrees and 180 degrees. So there's 2 of our solutions. Here, let's subtract 1 from both sides. And we'll divide by 2. And so we get sine is negative 1/2. Remember that sine is regular 1/2 at 30 degrees, which is right here. But we want the two places where sine is negative, and that is in this quadrant and this quadrant with those reference angles of 30. So let me use a different color here. This angle right here is going to be 180 plus 30, and that's 210. So the sine of 210 is negative 1/2. And then let's get this one too. This orange one is going to be all the way around 360 except for that last 30. So 360 minus 30, and that's 330. So there's two solutions, and here's the other two. That one actually had 4 solutions. Okay, I believe there's one more technique that I want to show you. We'll do both of these. This section is a little bit longer, but part of the reason just to show you one of each technique. So you might be able to tell that the one technique we haven't done is half angle. And how do I know that this is going to be a half angle? Because that theta over 2 is a half angle right there. Okay, so we need to know the half angle identity for cosine, and that is this one right here. Actually, they show you on this sheet. So let's go down to example 2. Half angles, they're doing sine, but it's actually cosine. The sine identity that you see here, cosine is the same, except instead of 1 minus cos underneath, it's 1 plus cos. So this is what it is. It's plus or minus square root 1 plus cos over 2. And we don't need to worry about the plus or minus because we're going to end up squaring it anyway. We do need to worry about extraneous solutions, so we'll deal with that shortly. But for now, I'm going to replace cosine of theta over 2 with this identity. And once again, I don't care about the plus or minus because the way that we're going to get rid of that square root anyway is to square it. So that's not really a big concern. We'll just put it there just for completeness sake. Okay, here's the other important thing. Before we square this, if we square it in its current form, that would be a bad idea because it's going to be very messy to have to FOIL out the right side. So here's my recommendation. First thing is move this over to the other side. So that way it makes it easier to square. So we have 1 plus cosine equals radical 3 times this thing. And you might say, well, that still looks pretty bad to square, but actually it's not too bad, as you'll see. So let's square both sides. How do we know to square both sides? Because we have this big square root and there's no way to get to it unless we square it. So as long as we do it to one side, we can do it to the other as well. And the only thing to keep in mind is because we were squaring both sides, we may have an extraneous solution. So let's FOIL this out right here. And when we FOIL, this is the left side that we're foiling, we would get 1 plus 2 cosine plus cosine squared. Okay, how do you square this side? Well, you first would start by squaring that, and radical 3 squared is 3. Next, you would square this, and whether it's positive or negative, no matter what, when you square it, it's just going to be positive. So that's why we didn't care about whether it's positive or negative. When you square this thing that's under the square root, it just disappears, and you get this. Okay, now how do we clean this up? Well, let's distribute this out. So 3 times 1 plus cosine would just be 3 plus 3 cosine. So all I did there was just distribute the 3 to both of these. And then we can simplify this by multiplying both sides by 2. Same thing over here. So this becomes 2 plus 4 cosine plus 2 cosine squared equals 3 plus 3 cosine. Let's move everything onto the same side right now. And I'm just going to put this thing in front because it's better to have the square terms coming first, a little bit easier that way. So minus 3 and minus 3, minus 3 cosine, minus 3 cosine. So 4 minus 3 cosine is 1 cosine, and 2 minus 3 is minus 1. So we get this right here. Now this technique is one of the early ones we've done, which is factoring a trinomial. That's technique 4. And you might be able to recognize the trinomial again just to verify. Pretend that the cosine was an x. That would be like 2x squared plus x minus 1. So how does that factor? Well, the only things that would multiply to 2 cosine squared would be 2 cosine times cosine. The only things that get minus 1 would be positive 1, negative 1, and I think it has to be the plus 1 there and the minus 1 there. If you FOIL that, you'll be able to tell it works out. It doesn't work if you did 2 cosine plus 1. Let me check that using FOIL. Alright, so let's solve this now. So this one's a little bit easier. Cosine plus 1 equals 0. We'll subtract 1 from both sides. Cos is -1. Where does that happen? Well, cosine is the x-coordinate, and the x-coordinate is -1 right there at 180 degrees. So 180 is one of our solutions. Let's do this one as well. We'll add 1 to both sides. 2 cosine equals 1. We divide by 2. We get cosine is 1/2. From that chart that you hopefully have memorized, the 60 degrees is the one that has a cosine of 1/2, but it's where cosine is positive. So cosine is positive here and here. That means this angle and this one that has a reference angle of 60, that's 300 minus 60. Sorry, 360 minus 60, which is 300. And then that first quadrant angle is also where cosine is positive. So those are 3 possible solutions, but when we actually plug them in, the reason we have to check and plug them in is because we squared both sides. And anytime that happens, you might get something extraneous. You can see that only 2 of them work, 60 and 180. 300, when you plug in that 300 solution, it ends up not working. It ends up being extraneous. Alright, I know this is a long one. The very last one I want to show you, because this one is a little bit harder. First technique I know we're going to use is double angle because of that 2 theta. So you can see that's technique number 1. And the identity for sine's double angle is this one right here. Sine 2 theta is 2 sine cosine. So I'm just going to replace that. 4 cos squared minus, how do you do this? Well, sine of 2 theta is this right here, and that's telling us to square it. So I'm literally going to replace sine of 2 theta with this, and then that's being squared, so I'm going to square it. Okay, so then let's do this. So we get 4 cos squared minus, if you square the 2, you would get 4, and if you square this, you would get sine squared cosine squared. And then let's move that cosine squared over to the other side. So we will move it over by subtracting it, so that goes away. And then we'll subtract it right there. So we would get 4 cos squared minus cos squared would be 3 cos squared. And we have minus 4 sine squared cosine squared, that's equal to 0. Which technique should we use? Well, there's probably more than one that you could use, but the easiest one to use here, because these both have cosine squared, we could factor the GCF out of that. So let's do that. We would have 3 minus 4 sine squared, and that's equal to 0. And now how do we solve this? We can solve it by setting both parts equal to 0. So cosine squared equals 0. Let's square root that. That means cos equals to 0. Where does that happen? Well, again, the cosine is the x-coordinate, and that equals 0 here, and it equals 0 down here. So 90 and 270 would be our solutions from this part, at least. And then what about the second part? So the second part is if we set this equal to 0, 3 minus 4 sine squared equals 0. We'll subtract 3 from both sides, and then we will divide both sides by -4. So we get sine squared equals 3 over 4. And then how do we isolate the sine? Well, we need to square root it, and we'll square root this and put a plus or minus in front. The sine equals plus or minus radical 3 over the square root of 4, which is 2. So in our chart, the angle that has a square root of 3, or a sine of radical 3 over 2, it turns out to be that turns out to be 60 degrees. But remember, it's both plus and minus here, so there's actually going to be 4 solutions to this, and I'll show you where they all are. So this is the 60 right here, but then we need all 4 places because sine is positive in those 2 and it's negative in those 2. So those are all going to be reference angles of 60. And the easiest way to do this, well, we know that one of them is 60. This one is 180 minus that 60, which is 120. Okay, this one right here is going to be 180 plus that 60, which is 240. And this last one is going to be 360 minus that last 60, which is 300. So we ended up getting 4 solutions there, and 2, those 90 and 270, the other one. So let's verify that this works out, and you can see there are in fact 6 solutions. 90, 270, those are from one side, 60, 120, 240, and 300. That's right down here. So 6 solutions, that's probably the maximum that you would see. But that's 13.5, that's the end of chapter 13. It is a lot, but the main thing, like I said before, is to practice doing it. The more you practice doing these, the better they get.